Hello, class. Welcome back to this class. I'm Mr. Douglas, and I'll be taking you through physics, and particularly interference of waves. Here, we want to know how waves interfere, the types of waves that we have, and we shall be looking at the different interference of waves in different cases, interference in sound, interference in water waves, and even interference in light. So welcome back, and I hope we will enjoy together. Now, we want to begin it is physics, and I've said that we want to talk about interference. Of waves. Now, class, when we talk of interference, this is one of the properties of waves. Now, if you can remember, we said that a wave is a form of energy transmitted from one medium to another due to disturbance of waves, due to disturbance of particles, sorry. Now, when you disturb, for example, a water particle, these water particles are set into vibration or into motion and actually transmitting energy, and that is what we call a wave. Now, we talked about, we have got different types of properties of waves. One being, like linear propagation of waves, that is waves. Yeah, another type of property of wave that we have, another property of waves that we have is interference of waves, which actually is our substrand today that of discussion. Now, when we talk of interference of waves, class, what do you understand by interference? What do we mean? Or rather, when we talk of interference, to interfere means what? Now, when we talk of interference, we know when we have two things or two substances meeting one another, that process is what we refer to as interference. And class, waves can also interfere. We shall be talking about the interference of water waves. Now, we are saying that interference occurs when two waves meet while traveling through the same medium. it occurs when two waves meet while traveling through the same medium. When two waves meet while traveling through the same medium, then interference is going to occur. In this case, the medium could be even water. Now, interference is an import of superposition. We have got the principle of superposition. So interference is an import of the principle of superposition, which is going to say that the principle of superposition states that, we want to see the statement of the principle of superposition that is going to guide, or rather govern, the interference of waves. Now, it states that the resultant displacement at any point the resultant displacement at any point is the vector sum of the individual displacement of the waves at that particular point. The resultant displacement at any point, the resultant displacement at any point is the vector sum of the individual displacements of the waves at that point. Individual displacement of the waves at that point. So what do we mean by this? That the principle of superposition, which says that the resultant displacement of any point is the vector sum of the individual displacement of the waves at that particular point. Now, class, suppose we have got two waves with different amplitudes. An amplitude is the maximum displacement of a particle in either direction of the mean position. Now, suppose we have got now two waves with the amplitudes A1 and A2. Now, these particular waves may interfere. These particular waves may interfere, and they are going to interfere either constructively or destructively. And that one will later give us actually the two types of interference that we have. Now, suppose the amplitudes of two waves pulses are A1 and A2. Suppose the amplitudes of two wave pulses are A1 and A2. That is two different waves having the amplitudes A1 and A2. Now, in this case, these particular waves are going to interfere, and according to that principle of superposition, we are saying that these particular amplitudes are going to interfere, and assuming that they are traveling in the same direction, these two waves with the same amplitudes A1 and A2 are traveling the same direction, traveling in the same direction, then we are saying that the resultant now amplitude, that's after interference, the resultant amplitude A is given by, will now be given by, that resultant amplitude A will be equal to A1 plus A2. That is, two waves having different amplitudes, that is A1 and A2. Now, these particular waves are traveling in the same direction. When they do that, after interference, they are going to combine and form one wave with an amplitude A. Now, the amplitude or the resultant amplitude A is a much larger amplitude. We say that a much larger wave is being formed, a greater amplitude, because you see, we are talking of the vector sum of the individual displacements, A1 plus A2. This is what we mean by the principle of superposition, that the vector sum of the two will give us the resultant amplitude. And this one class only occurs when the two waves are traveling the same medium and, of course, in the same direction. Now, we are saying that if, for example, if A1 is equals to A2, that is, the amplitude of A1 and A2 are the same, then when they actually combine, that is when they interfere, when the two waves with this amplitude are going to interfere, then the resultant wave, the amplitude of the resultant wave will be twice the amplitude of the individual pulse, will be twice the amplitude of the individual pulse. And so we are saying that if A1 is equal to that, the amplitudes are of the same equal amplitude. Now, then the amplitude of the resultant wave is twice the amplitude of the individual wave pulse. So, i.e., the waves have equal amplitudes, then the amplitude of the resultant of the resulting wave or pulse will be twice the amplitude of the individual wave pulses. Because now this A1 is equal to A2, then when you add them together, because we are talking of the vector sum, then the resultant amplitude now will be twice this the amplitude of the individual pulse. That's what we are saying there. Now, suppose class, now here the two waves are traveling like that. Okay, we can demonstrate using a diagram here to see what we are talking about here. When the two waves traveling in the same direction, the same medium, actually interfere. When they interfere, then we are saying that we may have a wave of this kind having that amplitude. This one is going to meet with another one here. So if this one is traveling in that direction, like that, in the same medium, they are going to interfere. Once they interfere, then the resultant wave will be having a much larger amplitude. So we are saying that from this end to this end, This is the amplitude, let's say A1, from this end to this point. We have got A2, amplitude 2 for this particular wave. Then when this one and this one combine, then they are going to give us a wave pulse of a much larger amplitude. This one here, that is now the amplitude A. This one we call it resultant wave pulse. Resultant wave. That is what we are saying there. Now that's a case whereby the waves are moving in the same direction. Now for opposite wave pulses, we have that now for opposite wave pulses means that maybe we have got the waves traveling in different directions. Traveling different directions. So we are saying that for opposite pulses, the resultant amplitude now will be given as, for opposite wave pulses, the resultant amplitude is given by A is equals to A1 minus A2. You know, in this case, the waves are traveling in opposite direction, and therefore the vector sum now is actually the difference. This is where now A1, the amplitude of A1 is taken to be positive and that of A2 negative. So because they are moving in different directions, we are going to find their difference for us to be able to get the resultant wave pulse. So if A1 and A2 are numerically equal, then the two wave pulses will cancel out and the resultant amplitude will be 0. And the resultant amplitude is 0. That is, if this one and this one, they are numerically equal in magnitude. If A1 and A2 are numerically equal, then we are saying that the amplitude of the resulting wave will be now will cancel the two wave pulses will cancel out and the resultant amplitude will be 0. The two wave pulses cancel out, and the resulting amplitude will be 0. That is, if this A1 is equal to A2, you see we are getting the difference. So if this one is equal to that, when you subtract actually here, you will get that there will be a 0 amplitude. So the A will be equal to 0. That is what you are saying there. Now, that is to say, for example, if we are saying that we have this, and they are just two but moving in the opposite direction. So we could also be having that. So this one is moving in this direction, this one is also moving in this direction. So at the end of the day, the resultant wave now will have a much smaller amplitude. You see the amplitude of this one now, this is the resulting wave. resultant wave. And you see this amplitude now is much smaller as compared to the individual wave pulses. That's what you're saying there. Or we can also have a case whereby the two waves now are going to interfere and to give us actually an amplitude which is actually zero. A case whereby now we have this one. We have maybe another one here. This one moving that direction. Now this one is have what we call a straight line like this. This is the resultant wave. You see, this is a crest and this is a trough. This one is going that way and this one is coming this way. When they are on to interfere, where at the point of interference, this one will cancel out with this one. That is, if they have the same amplitudes initially, they are on to cancel and then give us what we call a resultant wave of zero amplitude. You see here, this is just a straight line. It does not have what we call any crests or trough, and therefore we say that it is having zero amplitude. So that's what we have, and that one now will lead us to two types of waves. That one will lead us to two types of waves. Following what we have just discussed, we can have two types of waves. So, types of waves. So, from our discussions here, actually, class, you can be able to see that we have all two types of waves. For example, the previous one that I had drawn here, you saw that when two waves combine or interfere, we got what we call a wave pulse of much larger amplitude, but here we are getting a wave of a smaller amplitude, or nearly a wave with zero amplitude. So this one is called destructive interference, and the other one that I had drawn here actually was constructive interference. So therefore we have got two types of waves, that is constructive interference and two destructive interference. So we want to discuss each of these so that we are able to know what each means and how does it come about. So let's talk about constructive interference. Now, like we have seen, constructive interference is going to occur when two crests meet, or a trough and another trough of another wave meet. That is, the crests are aligning and the troughs also align. So this one occurs when two waves meet in phase, meaning their crests and troughs align. So it occurs when two waves meet in phase. Meaning crests and troughs align. That is to say, when a crest meet with another crest of another wave, or a trough meeting with another trough of another wave, in that case we are going to get what we call constructive interference. Now in this case, the result of constructive interference is that there will be a greater, there will be a resulting wave of a greater amplitude than the individual waves. So the result in wave, this results in waves with greater amplitude. This results in a wave with greater amplitude than the individual wave pulses. I think we have just demonstrated that one, but we can also demonstrate this with another diagram yet to be able to understand what we mean by constructive interference. So, i.e., suppose you have now types of interference. So suppose we have this one, and you have something like that. So we may have waves 1, waves 2. Those are traveling in the same direction, in the same medium, and they are going to interfere. At the point of interference, that is when a crest meets with another crest of another wave. We have said that we are going to have a resultant wave of a much greater amplitude. So we are going to have it this way. Let me use dotted line, dots like this one to show the resulting wave. Like that. So this is wave 3. So waves 1 is having this amplitude, as you can see. Waves 2 having an amplitude which is slightly greater than the amplitude of wave 1. But now wave 3 will be as a result of the interference of the two waves. That's the crest of wave 1 plus the crest of wave 2 interfering to give us this other wave having a much larger amplitude. That is wave 3. And so we are saying that the resultant wave 3 is the sum of the amplitudes of the waves 1 and 2. The resultant wave 3 we are saying that is the sum of the amplitudes of the waves 1 and 2 is the sum of the amplitudes of waves 1 and 3 and 2, sorry. So when 1 and 2 meet, they are going to give us the resultant wave 3, which is of much larger amplitude. Now, what about destructive interference? This is now constructive interference that has occurred here. You see we are getting a much larger amplitude. What about destructive interference? Now, like we have seen in our previous discussion, destructive interference is going to occur when now two waves are interfering, but they actually meet out of phase. So it occurs when two waves meet out of phase. It occurs when two waves meet out of phase, meaning the trough of one wave is going to meet with a crest of another wave. When that one happens, now they will cancel each other, actually causing destructive of the individual waves. So the crests of one wave will align with the trough of another, meaning the crest of one wave aligns with the trough of another. The trough of another, i.e., you can also have a diagram to show that. You know, in destructive interference, the waves are going to be destroyed completely, so that we have a wave of zero amplitude. So we may have a wave of this kind. So as you can see, we may have wave A, this is wave B, and this one here, that straight line, that horizontal straight line is the resultant wave 3. Resultant wave, let's say wave C. Now, what we are saying is that these crests will meet with this trough, and when they meet destructively. That means that this one, the amplitude of this one will cancel with the amplitude of this other wave, giving us what he calls a zero amplitude. That's a wave of zero amplitude. So there will be no crest, no trough for the resultant wave. That is what is happening in this particular case. So the two waves, waves A and waves B, wave A and wave B, are going to meet such that now they actually interfere destructively. They are going to actually interfere destructively, giving us a resultant wave C of zero amplitude. That's what you're saying there. Now, in a ripple tank, when, for example, when you have got two similar spherical dippers, those small balls, you adjust them such that now they are attached to a vibrator, and then they touch the water surface in a ripple tank. What happens is that they are going to produce coherent water waves. Coherent water waves, meaning that waves of the same frequency and amplitude. So when two similar spherical dippers are attached to a vibrator in a ripple tank, then they produce coherent water waves. When two similar spherical dippers are attached to a vibrator, you know, they are going to produce what you call coherent waves. So in a vibrator and a ripple tank, they produce coherent waves. When we talk of coherent waves, we are referring to those waves that have the same frequency and a constant phase difference. So coherent waves have the same frequency and constant phase difference. They have the same frequency. The word coherent means same. So they have got the same frequency and what we call constant phase difference. So we are saying that as the waves now interfere or overlap, they create a pattern of alternating bright and dark fringes or dark bands. So as the waves overlap, they create a pattern of dark and bright fringes or bands, dark and bright bands or fringes, i.e. we now have something like this. Maybe this is a dip at this point. So this particular dipper is this spherical dipper, a ball dipper, which is round. So it's going to touch the water surface and then produce waves of this nature. Which are circular. Yet we may have another spherical dipper there, which is going to also produce waves, so that now these waves are just like that. And as you can see, these waves are interfering. At the point of interference, we are going to have what we call bright lines depicting constructive interference, and these other lines where there is no that interference, we are going to have what we call destructive interference. So we are going to have along this, there is constructive interference there, but around this one here, there is destructive interference. Yet this one is also around this one here, there is constructive interference. Then they will be alternating with destructive interference. So these particular waves are going to produce alternating constructive and what we call destructive interference. That is what we are seeing there. And at the points where they are interfering, these points here, that's where we have constructive interference. And at this particular point here, where they seem not to be interacting, then we have got what we call destructive interference. And remember, these are water waves. So the bright bands are going to appear along these particular solid lines, and the dark ones are going to appear along the dotted lines. That is what you are saying there. Now, if you placed, for example, a cork, at this particular point where we have constructive interference, the particles are going to be disturbed so much so that now if you placed a cork at this particular point, then there will be what we call that cork will be jumping up and down, showing disturbance. And if you place that cork along these points here where there is destructive interference, where water is actually still, the cork will be undisturbed. That is what we are saying there. Now, class, we are saying that the bright bands are due to the bright bands that we are going to observe here at the constructive interference will be due to constructive interference, and the dark bands will be due to destructive interference. That is what you need to understand in this case. Now, having talked about that, I would like to briefly talk about interference in sound waves, so that we see how also it takes place in that particular case in a short while. Just interference in sound waves, having looked at the water waves, so interference in sound waves. So class, sound is also a wave, and it can also undergo what we call interference. Now this one is going to be demonstrated by connecting two speakers in parallel and to the same audio frequency generator. So it can be to the same audio frequency generator. i.e., we may have, let me draw a simple diagram. So at this end we have an observer moving along this line, call it XY. So at this point, the complete lines are going to demonstrate, or rather to show, will be the points of constructive interference, and the dotted ones will be showing the points of destructive interference. And therefore, here we are going to have destructive interference, constructive, destructive, constructive, alternating, and this is the audio frequency generator. This is speaker A, and this is speaker B. Now, what are we saying here? We are saying that if you connect the two speakers to the same audio frequency, like we can see now, that these particular speakers are going to act as coherent sources. That is, they are synchronized because they are connected to the same audio frequency generator. So we are saying that the connection of the two loudspeakers to the same audio frequency generator will make now the two speakers to act as synchronized or coherent sources. Makes the speakers act as synchronized or coherent sources. Now the coherent sources here will mean that they will satisfy three conditions. Now we are saying that they satisfy the following conditions, meaning they satisfy three conditions. One, that they have the same frequency or wavelength, they have equal or comparable amplitudes, and also they maintain constant phase difference. So have the same frequency, or wavelength. Two, they also have equal or comparable amplitudes. And three, they have what we call, they maintain a constant phase difference. So they have constant phase difference. So for them to be coherent, then they must have the three conditions: same frequency or wavelength, equal or comparable amplitude, and also maintain constant phase difference. Now if an observer was moving along XY, along this one here, you know, he will be able to observe what we call alternating loud sound and soft sound. That is, at one point there is soft sound, at another point loud sound. So at the regions or points marked C, there will be constant loud sound, and at the points marked D, there will be constant soft sound. That is what we are saying there. So an observer moving along XY experiences alternating loud sound and soft sound. So the loud sound will be due to constructive interference, and the soft sound will be due to destructive interference. The loud sound is due to constructive interference, and the soft sound is due to destructive interference. So meaning that as you move around the speakers, especially along the line XY, then you will be experiencing varying sound intensity. That means that at the constructive interference there will be loud sound, and at the destructive interference there will be soft sound. So as you move along, the soft sound and the loud sound will be alternating with the one another. Now, the sound is weakest where there is complete destructive interference. I think that is what you need to understand, because as you move, there is a point whereby you will not get any sound at all. At that particular point, we say that the sound is weakest, and at that particular point, there is what you call complete destructive interference. Complete destructive interference. That's what you need to understand. Now, what do you think will happen if you increased the frequency of the audio signal generator? If you increase that particular sound, that's frequency at this particular point, so that the frequency now is so high. If you increase that particular frequency at this particular point, what will happen is that the points of destructive interference, will appear to be very close to one another, and so is the same way for the constructive interference. That means point D and D will move closer together, and point C and C will also be very close together when you increase the frequency of the signal from the generator. So class, that is what we have talked about here, about interference. So get to understand that we have got two types of interference, that is destructive interference and constructive interference. We said that constructive interference occurs when a crest meets another crest, and destructive interference will going to occur when a trough meets another trough. A trough meets a crest of another wave. Now, we have said that interference can be able to occur in both this water waves, sound waves, and even in light waves. Now, like in this case, under the sound waves, we have said that if you connected the two speakers to the same audio frequency, you will make the two speakers act as coherent. This word here, act as coherent or synchronized source of sound. And what do we mean by that? That the two speakers now will be having the same frequency. The sound from the two speakers, from each speaker, will act as what we call, will have the same frequency or wavelength. They will also have equal or comparable amplitudes, and finally they will have to maintain constant phase difference. These are the conditions that you need to know when you want to talk about coherent source, because you'll be told to state three conditions that actually satisfies the concept of coherency. So they must have the same frequency or wavelength, have equal or comparable amplitude, and maintain constant phase difference. Up to that point, class, I want to stop there. Hope we have enjoyed the lesson, and go and read more about this one so that you get to understand actually in detail what interference of waves mean. Otherwise, I want to stop at that point. Thank you so much, and enjoy your time.